I want to go through some more topics in introductory differential equations to get you, partly get you ready for the rest of the homework. I've been concentrating so far on one of the ones that, of course, the book also concentrates on. I've been using P up till now, but let's use Y just to be different, or just also kind of go more with the book. Y prime equals ky. Here y we'll think of as a function of t. And what we discovered is that there are functions that have this property, that that's when you take the derivative of function y, you get a constant times itself. And the ones that we know about are some totally random constant, unrelated to k, times e to the kt. And it turns out those are the only ones, although we haven't really completely been, we couldn't really be completely sure of that. And one thing I hadn't done yet is talked about the graph of that, and talked about how there's a graphical interpretation of this. And we're going to talk a fair amount about that, and actually use some kind of cool computer programs. But if I look at all the different functions, y equals c to the kt, well, if c equals 0, for example, that's just 0. If c equals 1, maybe it's like this, c equals 2, c equals 3. C could be negative as well. That doesn't describe population growth really well, but there's plenty of things where that makes sense. For example, if you talk about your net worth and you owe a lot of money and you pay a lot of interest, it turns out that it often looks like this, which is not real fun. That's why it's not so good to be heavily in debt. And so if you choose all those different constants, it just takes e to the kt and multiplies it. And that's what happens when you multiply by a function. It just makes it either bigger or smaller in the y direction, or flips it around the y-axis. And let's think about how all of these really do embody the same idea. Now here, I happen to choose, let's just be a little bit more specific, and let's say k is greater than 0. Or even, to be really specific, maybe k equals 1. Okay, so maybe this is e to the t, and not e to the kt. Then this is just a very familiar function, the exponential growth function. And let's see if it really satisfies this equation graphically. What does this mean if I just look at like y prime equals y, the most basic version of this with k equals 1? It's really, really important to remember that these have geometric meaning. Y is the height of a point in the plane above the x-axis, and this is the slope of the curve that's supposed to go through that point. And so this equation says I'm looking for a curve that always satisfies this very special relationship, height equals slope. Well, let's see if that makes sense. Well, here, let's look at this one curve. The height does equal the slope given a certain, well, if the height is this, the slope is here. As the height gets bigger, the slope gets bigger. As the height gets bigger, the slope gets bigger. And it's plausible that this curve has that property, that as it gets higher, it gets steeper. And in fact, this is a perspective we had way back when we first analyzed and we first tried to figure out what might be going on with the exponential function. We actually went backwards. We drew the exponential function, and we observed this property about it, that as it gets higher, it gets steeper. And so when we took a very rough graphical derivative of it, we got something that looked very similar. And then we used the calculator to see that it actually really is exactly its own derivative, not just approximately. Well, here I have the same kind of thing. Here I'm taking this function, I'm scaling it up, I'm making it that much taller, but I'm also going to make it that much steeper. And it turns out, if I scale them up both by a factor of c, it still has this property, that at every point the height is equal to the slope. And similarly here, negative height, negative slope, more negative height, more negative slope, steeper downhill. It seems to have the right shape to be y prime equals y. So we're going to go back, and in the next section we're going to talk about a way to really codify this and talk about the graphical way of solving and understanding solutions to equations. Let's look at another simple one. If I have, let's say, the other kind of differential equation we've already seen is actually when I have s is position, v is s prime is velocity, and a is s double prime is acceleration. Then we've talked about how in nature often you know information of the acceleration because that's directly linked to the force that's on something. And then you integrate twice to get the position. The simplest example was s double prime equals like minus g is the downward acceleration of gravity. And we know what the solution for that was. It was s of t is minus 1/2 gt squared plus v naught t, our initial velocity, plus s naught. It's not an accident that in this case it was what's called a first order differential equation. It only involved the first derivative. And there was one arbitrary constant that gave us a whole family of different solutions. And here it's a second order differential equation. It involves the second derivative, and we got two constants that we're going to need to figure out to solve that. But right now I want to focus a little bit more on the geometry of it. What do these look like? They look like downward going parabolas like this. Woo, boom. Okay. Or maybe they just always have the same kind of coefficient here, but you can play with the height like this. You could play with the horizontal position, but let's just play with the height for now. So those are that's again a whole family of curves that satisfies this differential equation. So this is really our home base that we've started with before. The difference between this kind of equation and y prime equals ky is here s is an unknown function, but I'm explicitly telling you what the second derivative is. It's just minus a fixed number, the acceleration of gravity. And then we got an explicit formula for v and an explicit formula for s by just integrating twice. Solving general differential equations is a little bit harder. Here, y prime equals something, but this is not a given function of t. It says there's a relationship between y prime and itself. But you can't just say, oh, therefore I'm just going to integrate both sides, because this isn't already a given function of t. It has the unknown in it as well. So here, the unknown appears only on one side of the equation. That's always simpler in terms of algebra. Here, the unknown appears on both sides, and it's going to be harder to solve those in general. We're not going to do a lot of solving of these, but we're going to find a couple of techniques that let us solve a fair number of those kinds of equations. But actually solving it in general is going to be hard. This one, we kind of guessed the answer. We kind of knew. We had already seen this function have this property, so we were able to guess. In general, we're not going to be able to guess. So that's a little bit more about the general ideas here. And in the next video, I'm going to be a little more specific about how you would get down to the algebraic nitty-gritty. But let me go ahead and save that for the next one.